3D is too easy, bump it up to 40.
40.
Around 5D.
All right, so we are doing, this is the last section in 7.2. So I split 7.2 into 3 lessons, and this is the last idea that's in the one section of the book that they put all together. So we're doing volumes again using a known cross section. So they will tell you what shape your cross section will be. So we've only worked with circular cross sections with the discs and the washers. So you can basically do the same thing and use area to help you find volume, but picking any cross section that you want besides a circle. So common ones that we'll work with will be squares, which the area of a square is side squared, rectangles, base times height, equilateral triangles. This formula is derived from 1/2 base times height. So you could always use 1/2 base times height for the triangle, but because an equilateral triangle has 3 sides that are the same, and the angles are 60, 60, and 60, it works out so that there's a 30, 60, 90 in there when you try to find the height, and that's where the square root of 3 over 4 comes from. So square root of 3 over 4 times side squared, and then semicircle is half a circle, so pi r squared over 2. You don't get a formula sheet for the test in here, so you're going to need to know these formulas. And probably the only new one would be the square root of 3/4 times side squared. Okay? Here are some examples of, wipe that off, known cross sections. So let's see. This one, they're bounding in between the x-axis and the equation y equals x squared, and these would be semicircles. So notice that the semicircle is like coming out. It's 3D. It's coming up at you. But the distance from y equals x squared, you know how we'd always draw that representative rectangle? We're still going to do that today. But the bottom of the rectangle that's touching the curve to the x-axis is the what of the circle, of the semicircle? It's the diameter, because it's going all the way across. So the diameter of the circle is the top minus the bottom in this case. Gosh, it's kind of hard to see. I think those are squares, but you've got the same curve happening, y equals x squared to the x-axis, and their perpendicular cross sections are squares. So the top of the curve to the bottom of the curve, that representative rectangle, is the side of a square. I can't tell if that yellow one, I can't tell if they're triangles or if those are rectangles. The bottom one are rectangles. There we go. So the bottom one are rectangles. So you've got the bottom of, or the side of the square, which is like the height of the rectangle laying on the top minus the bottom of the curve. And I think you're right. I think the top one is some sort of a triangle. I can't tell if it's equilateral or right from there. Here's another view of, I can't tell what the equation is on that, but these would be perpendicular cross sections that are squares. Another example of semicircles. And then that one would be isosceles triangles. One of my former students, Royden Pugh, made this for me on his 3D printer, but he made it like, he came back and visited the next year and brought this to me, and I was like, oh my God, this is so cool. So while you guys were working on your quiz, I traced it up here. So the bottom, so it's sitting on the x-axis at 0, 0. And this curve here in 2-dimensional land is y equals x squared. This curve here is y equals the square root of x. And the cross sections that are laying between there coming out at you are squares. And so the idea behind this is if you found the area of each square and added them together, you would potentially have the volume of your object. But remember that your dx, the width of your shape that we're working with, remember we're trying to get infinitely close to 0, even though you can't touch 0. So we're trying to shove as many of them in there as we can. So that's what we're doing today. So really fun. What? All right. So volumes of solids with known cross sections. So if you're taking it, make sure you read carefully on the problems. You're either going to be taking them perpendicular to the x-axis or perpendicular to the y-axis. If it's perpendicular to the x-axis, we're going to have the bounds a to b, and then times a of x dx. When we were working with the discs, we had pi r squared. The pi was out front, and the r squared, that, pi r squared was the area because it was a circle. This is just a more general formula for any shape. And then we use specifically the cross sections for each problem. Perpendicular to the y-axis, they just changed it to C and D, and then a y dy. So we're going to do our first one. The base of a solid is a region enclosed by the semicircle y equals the square root of 16 minus x squared and the x-axis. Cross sections perpendicular to the x-axis are squares. Find the volume of the solid. So the first thing that we need to do is we need to graph our semicircle y equals the square root of 16 minus x squared. So if we were to kind of undo the problem so you can see it as the equation of a circle, how would you get rid of the square root? You would square it. So you would have y squared equals 16 minus x squared. And then remember, with the equation of a circle, it's x squared plus y squared equals r squared. So you'd move the x squared over to the other side, and you would have y squared plus x squared equals 16. So the radius of the circle is what? The radius of the circle is 4. And if I were to just have given you the y squared plus x squared equals 16, if we were solving to isolate y, we'd subtract that x squared over, and you'd have 16 minus x squared. And then when you square root it, how many answers does it produce? It produces 2, a positive and a negative 16, square root of 16 minus x squared. So you get the top half of the circle is the positive square root, and then the bottom half of the circle is the negative square root, because this is saying we want y's to be positive half of the circle. So your y's are positive up top, and then the negative would be down below. Does that make sense? So they're giving you a semicircle because they only gave you the positive square root. So sometimes they won't tell you that it's a semicircle, and they'll just give you the equation, and you have to understand that this is half of a circle. That's why I went through this. All right? All right. So what's the center of our circle? 0, 0. So from the origin, we're just going to go left 4, right 4, and up 4, and that'll be our radius. 1, 2, 3, 4. 1, 2, 3, 4. 3, 4, and then do your best job to make a half circle there. So this is, if you're thinking 3D, this is the bottom of our cross, or of our shape. Let me grab my gray. Bless you. So the bottom of our shape is half of a circle, and then we are going to be filling it with cross sections that are what shape? Squares. And I don't think I have a semicircle cross section, but I don't have a semicircle shape with a cross section of a square as an example. I think they all use a quadratic. Yeah. All right, so first thing that I want you to do is I want you to draw your representative rectangle. And so if we're, I'm a horrible artist, but like, don't, it may, that would be that. This part of the rectangle, this part of the square is the rectangle that you guys just drew. And so the bottom of this rectangle here is touching the x-axis, which has the equation of what? Y equals 0. And then the top of this rectangle is touching what curve? y equals the square root of 16 minus x squared. So that's what you guys need to understand, that that rectangle that we just drew is the side of your square. Are we good with that so far? All right, so since our cross section is a square, give me a moment and let me get this out of there. All right, so I like to go to the side and work with my area formula before I put it in my integration, because we want to, if we can clean up the area of our equation first before we put in our integration, it just makes it easier later. So area equals side squared, because our cross section is a what? It's a square. So area equals side squared. So we have to come up with an equation for our square, which represented the rectangle that we've drawn, which is this 3D model for you guys. So the top of your rectangle, the side of your square touches the square root of 16 minus x squared. And then the bottom of it touches 0. So the square root of 16 minus x squared minus 0 just leaves you with the square root of 16 minus x squared, because it's top minus bottom. And then the square root of 16 minus x squared squared just leaves you with 16 minus x squared. So that expression, 16 minus x squared, is our area representation for our cross section that's a square. And now we're going to use this in the volume formula. So your volume, a to b of a of x dx. So we need our bounds. We are stacking or filling those squares between what x values? -4 to 4, because of the radius of our circle. Our side squared was our a of x that we cleaned up to become 16 minus x squared. And now we're ready to integrate. So the antiderivative of 16x minus the antiderivative of x squared, x to the third over 3, valuing from -4 to 4. So you do the same thing that we've been doing, f of b minus f of a, plug in your upper bound and your lower bound, subtract the 2, gives us 256 thirds cubic units. The cross sections that are squares are usually the easiest ones to do, because their formula is not like super complicated. All right, this next one. Find the volume of the solid, it's a solids, but should say solid. Find the volume of the solid, bless you, whose region is bounded by the lines f of x equals 1 minus x over 2 and g of x equals -1 plus x over 2 and x equals 0. Cross sections are perpendicular to the x-axis again, so that tells you it's going to be a dx problem. And this time we're working with equilateral triangles. All right, so let's go ahead and graph. I'm going to do the first equation in green and the second equation in blue, so we can see where our rectangles touch. So remember, f of x and g of x are just fancy for y equals. I'm going to rewrite that first equation so it's in mx plus b form. We'll have y equals -1/2 x plus 1. And g of x would be y equals 1/2 x minus 1. So that way our brains see it better. So we can pick out our y-intercept and we can pick out our slope. So our first one, y-intercept is what? 1 with a slope of down 1 over 2. So we've got, I'm going to actually make this a little bit bigger. I'm going to have every 2 units. No, I don't want to confuse myself. I won't make it bigger. Because I was thinking, oh, then I'd down 1 over 2, then I'd have to do a half, and I don't want to do that. Anyway, all right, so positive 1, just make sure that you get your slope correct. It's a down 1 over 2 on this guy. So down 1 over 2, down 1 over 2, you need to extend it. And then our blue guy has a y-intercept of -1 with a slope of positive 1/2. And then we are also bounded by the line x equals 0, which is essentially just your y-axis. So the bottom part of our shape that we're stacking our equilateral triangles in is a triangle. And then we're going to be having equilateral triangles coming up at us. So let's go ahead and draw in our representative rectangle. And keep in mind that your representative rectangle is the bottom side of your equilateral triangle. So, oh boy, let's see if I can do this. Oh, totally missed that dot. Nope. No, hang on. Oh, dang it. Boom, 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 boom. You guys get the idea?
Triangle.
Yeah. It's supposed to be 3D. Yeah. All right. So the top of the rectangle touches the line y equals, that's our negative guy, so -1/2 x plus 1. And then the bottom half of the rectangle, or not bottom half of the rectangle, but the bottom portion of the rectangle touches the green y equals 1/2 x plus 1. I guess I probably should have done that in black since our rectangle is black. All right, so we go to the side and we're working with the area for an equilateral triangle. So area equals the square root of 3/4 times the side squared. So our side on this one, so we'll have a square root of 3/4, and our side is that rectangle. It's the bottom side of the equilateral triangle. All 3 sides are the same. So essentially it's, what was that guy, f of x? The blue is f of x. So really f of x minus g of x. So if you wanted to write that, f of x minus g of x, and this is going to represent the side. So f of x was the blue, -1/2 x plus 1 minus the quantity +1/2 x plus 1. So we're trying to find this expression for the side of our square, or not square on this one, equilateral triangle. So we need to clean this up. So square root of 3/4 out front. Make sure that, yep, thank you, totally, yep. Need the square there for a side squared. Thanks, Green. Oh, did I write it wrong?
The second equation.
I did write it wrong, thank you. I was going off that guy. Thanks, guys. Give me a moment, let me erase. Hopefully I don't erase too much. There we go. There we go. Thank you. So now we have to distribute the negative to the negative 1/2 x and the negative 1. So you have negative 1/2 x in blue and another negative 1/2 x, which gives you a total of negative x. And then you had a positive 1 from the blue, and then when you distribute the negative to the negative 1, it's another plus 1, so 1 plus 1 makes 2. And then don't forget the square like I forgot earlier. All right, so then we can either, do you want to FOIL it or do you want to use U substitution? I always think if you can FOIL it, it makes it easier because then you end up with a polynomial that you can power rule rather than doing U and du and replacing and changing U bounds. All right, so let's go ahead and FOIL that. So negative x plus 2 times negative x plus 2, negative x times negative x, positive x squared, a negative x times a 2 gets you a negative 2x, and then you're going to have another negative 2x, which makes your middle term negative 4x plus 4. That quantity is no longer what? Squared, but we still have that square root of 3/4. So this whole expression represents the area of one of our triangles. Okay, are you guys with me? Now we plug it in the volume formula. So volume equals the integral from a to b of a of x dx. All right, so our a to b on this one, our bounds go from the leftmost triangle would be at an x of 0, and then they intersect at 2. Do you want to put the square root of 3/4 in front first or second? I mean, like, yeah, I don't care. We can do it in 2 steps or 1 step, doesn't matter. But that square root of 3/4 is a constant that can go in front of your integration. So square root of 3/4 from 0 to 2, and a of x is now x squared minus 4x plus 4. dx. All right, square root of 3/4 times x squared becomes x cubed over 3, and then minus 4x, add 1 to the power, which gets you to a 2, then divide by 2, minus 2x squared plus 4x, evaluated from 0 to 2. So you plug in your 2, your 0 would wipe everything out, ends up being 2 root 3 over 3 cubic units. So I don't know if I have a triangle one coming at you. These are right isosceles. This is right isosceles. Right isosceles. So here's a right. It's not very good. I don't know what curve they used. I'd have to trace it, but they didn't quite do a very good job. So this would be a cross sections of a right isosceles triangle, and you can see as the distance from the curve to the x-axis or whatever you're bounding it between, as those curves change, the sides of your triangles are changing. So if it's equilateral like we just did, so here's an equilateral triangle, as the distance between the curves change, the heights of those equilateral triangles will get bigger. So this one, I actually drew like a really nice 3D picture of it. It's like a triangle because the bottom of it was a triangle. So then we have triangles coming, but so like the back is, because this distance is bigger than this distance, so the triangles closer to the y-axis would be taller and wider as they come down at you. That's why this is kind of hard, like 3D and 2D land. You want to see my cool picture I drew? You can see it later. All right, next one.
You should replicate it.
Do what?
Replicate it.
You want me to?
That probably took you hours.
Well, it didn't take me hours, but I really have to look at my drawing to draw it. Do you guys want me to, or are you like, yeah? Yeah? Jeff, are you just saying that?
I agree.
Draw it?
Yes.
All right, hang on. I had to change my perspective here. So this is the y-axis, -1 to 1, and then the x-axis, and then we had, that's the bottom, and then I drew, let's see, a little guy here, and here, and then I have, oh boy. Give me a moment to shade. Shade. Colors, yeah, choose now, choose a light gray. Let's use a darker gray. Darker gray over here. On the side. No, it's not very good. So like you see equilateral triangle in the back, and you see triangle on the side, triangle on the other side. This is the top, and then your cross section. I lost my accent there. It goes like these. Cross here goes like these. That's the bottom, and then it comes up and you touch here, and then go like these. Go like this. Like this. Yeah, yeah. Sections like that. Look, pretty good. Not bad. I was under pressure. My Russian came out. All right. All right, next one. The base of a solid is the region enclosed by y equals negative x squared over 9 plus 4. So this is a quadratic. It's got, you've got your rocks. So that's why our graph is opening down. You're shifted up 4. And then it's being vertically stretched, just getting vertically shrunk by a 9th. So that's why it's looks a little bit wider, because it's being compressed vertically. And then y equals 0. So we are taking our cross section, so our shaded area in gray, hang on, gray would be, I did a gray highlighter. Guys, I didn't know you could do that. That would have been good for my drawing just then.
We'll teach you this in smart boards.
They did it. It was Smart Board 201. 201. That's when you get your doctorate. Huh? Uh-huh. Yeah. Yes, multiple Smart Board classes. 100 level, 200 level, 300 level. I don't want to restart. All right. So that's the bottom of our solid. Cross sections perpendicular to the x-axis again. And this time we're working with rectangles. So let's draw our representative rectangle for our cross section. That is a rectangle. All right, so our cross sections are rectangles that have heights twice that of the side in the XY plane. So the XY plane is the two-dimensional parabolic bottom. I didn't say it's a semicircle because it's not part of a parabola. And then the part that's down is this. So the height that's coming up at us it has heights twice that of the side in the plane. So if you think rectangles as base times height, the base is the rectangle that's running from the top of the quadratic to the bottom. And then the heights coming up at us, oh boy, are twice that. That looks like a triangle. I don't want a triangle. Guys, come on. Give me a break. All right, so the heights coming up at us of the rectangle are twice. No! Are twice this guy. So this is the base. This is our height of our rectangle, and the heights are twice the base. Are you with me? Okay, so height is, okay, or not 2b, but all right, so b times 2b. What did you say? You making fun of me? Did you have another joke? Oh. All right, so b times 2b gets us 2b squared. Okay, so b is the base of the rectangle cross section, and it's like the side of the square or the side of the equilateral triangle that's laying in there. So it's the parabola, which was y equals negative x squared over 9 plus 4. And the x-axis, which is y equals 0. So negative x squared over 9 plus 4 minus 0, if you want to write that in. You don't have to. But negative, let me put it right. Negative x squared over 9 plus 4 minus 0. Close it, square it, because this is b. Just leaves you with the negative x squared over 9 plus 4 quantity squared. So if you don't want to put that minus 0 part because you can see that, I think it's obviously going to be what it is, that's fine. But before we go into the integration, what should we probably do with our base squared? Boil it up. Times squared over 9 plus 4. So a negative times a negative gets us a positive. X squared times x squared is x to the fourth, and 9 times 9 is 81. So x to the fourth over 81. The outer and the inner both give you a negative 4x squared over 9. Gives you a total of negative 8x squared over 9. And then the 4 gets us plus 8. 4 times 4, 16. So that's the side of the base now squared. Still in front, the 2. Don't distribute that in because what can we do with it? We can pull it out in front of our integration. All right, but we do need our bounds. So it looks like they're crossing where? It looks like they're crossing at negative 6 and 6. To check, we would set 0 equal to negative x squared over 9 plus 4. They will be crossing at that, but just so in case you're like, ooh, I'm not quite sure, I don't want to get it wrong, so I'm going to double check. Solve for x. I'm going to add x squared over 9 to the other side. And then you have x squared over 9 equals 4, so you cross multiply. You get x squared equals 36. Square root it, we get x equals plus or minus 6. So that's just like a little verification check that our bounds were negative 6 and 6 on that. All right, so volume equals, she's going to go in front, -6 to 6 of x to the 4th over 81 minus 8x squared over 9 plus 16 dx. Done a good job of like reinforcing that if you have more than one term up in your integration, you really should have it as a quantity before dx. I just kind of, because some of, if you noticed on the quiz that I gave back to you, some of you set of brackets around that. You guys didn't count off or anything, but it's just appropriate to have it. All right, so power rule it up. 2 times x to the 4th will be x to the 5th over 5. 81 times 5. Anybody already work it out? 405. So x to the 5th over 405. Then we get an x to the 3rd over 3, and you guys should know 9 times 3. So -8x cubed over 27 plus 16x, evaluated from -6 to 6. This was not a neat one. 1,024 over 5 cubic units. Last one. The base of the solid is the region enclosed by a semicircle with a radius of 3 lying flat on the x-axis. Cross sections perpendicular to the y-axis. So this time we need the bounds are c and d, and it's a of y dy. And we're working with squares again. Find the volume of the solid. So make sure that perpendicular to the y-axis, dy, and then our area is going to be side squared. So the bottom of our solid, the base of our solid is a semicircle with a radius of 3. Let's go ahead and graph that. Oh, all right, so the equation of, if we had a full circle, what would the equation of our full circle look like? X squared plus y squared equals 9, or y squared plus x squared, using x's first. All right, so keep in mind, they want to be perpendicular to the y-axis. So that means our equation needs to say x equals. So instead of doing the y equals with the square root, we're going to have x equals. So we want to isolate the x. So that means we're going to subtract the y squared over. So we'll have x squared equals 9 minus y squared. And then to get rid of the square, we square root it, produces how many answers? 2. So we have x equals positive and negative times the square root of 9 minus y squared. So think about what this is telling you here. On the first example, let me flip back here. On the first example, this plus minus situation, the positive square root, it's saying that you want your y's to be positive. So all of the y's are positive above the x-axis here. And this portion is saying the negatives, which is below the x-axis, right? Okay, so on this next one, this is saying it wants x's to equal positive values and x's to equal negative values. So where are your x's positive? To the what of the what? To the right of the y-axis. So this portion, the positive root, is here. And then the x's that are negative are to the left of the y-axis. And the reason, let's put my gray up and shade in. So the reason that I color coded that, because our representative rectangle isn't vertical, it's horizontal. So the right side of that rectangle is touching which portion of the root? The positive, and then the left side of the rectangle is touching the negative. All right. We're going to go over that our cross sections are squared in this one. So area equals side squared. My arc again. This church would have fit. A wonky square, but all right. So the right side of it is touching that one. So it's x equals the square root of 9 minus y squared. And then the bottom is the red, and it's touching x equals negative square root of 9 minus y squared. So when we go to do the side, it's really the right, which I have in green, right minus left. So we've got to use the square root of 9 minus y squared first, minus negative square root of 9 minus y squared. Substitute it. All right, so let's clean it up. So the minus the negative really becomes a positive. So how many of those quantities do we have? 2. So we have 2 times the square root of 9 minus y quantity squared. So this is really, you don't need to FOIL. So you'll square the 2, which gets you 4, and you'll square the square root, which what happens? They cancel, so you're left with that quantity on the inside. So we'll have 4 times 9 minus the y squared. I would not distribute the 4 in, because when we go to write the integration, what do you do with the 4? Put out in front. Now, when you go to write your integration, volume equals, our bounds are now c to d a of y dy. Make sure that you use c and d bounds, that you use y values. So we're not negative 3 to 3. They're stacking up horizontally on the y-axis from 0 to 3. So we're going to have, it was a 4 out front, so 4 times the integral 0 to 3, and then 9 minus y squared dy. So integrate 4 times the quantity, 9's antiderivative is 9y minus y to the third over 3, evaluated from 0 to 3, gives us a total volume of 72 cubic units. Bada bing, bada boom. All right, find your worksheet. So it's not bookwork for this day, it's worksheet, should be in your packet.
Just one paper.
Yeah, it's just one paper. Do not do your work on the worksheet.